Hey everyone, this is Suthar, and today we will learn about what is a subgroup. So in this today's session we will discuss group examples, what is a subgroup, and some of the examples based on that. So first, what is a subgroup? Okay, as by its name, it's the first one. What is the condition, or what is the definition? So see, if G star, it is a group and H is a subset of G, that is this H is a subset of G. Okay, and this H star is also a group. Okay, then it is called then this H star, it is called a subgroup of G. So what is the condition? First, the main group G star has to be a group. Okay, then second, H must be a subset of G, and also this H is also a group, right? Then we can say that this H is a subgroup of G. Okay, now for example, let us do that. Show that this Z plus is a group. So actually it is a sum of group. So fine, now we know that what is a group. So what are the conditions? So the first one is the closure property, then the second one is the associative property, existence of identity, and existence of inverse. So we will simply do that. It is very easy. Now the first one, the closure property. Now Z means set of integers. So as you can see, for every AB belongs to Z, we get their addition belongs to Z. So it is very obvious. So therefore closure property is satisfied, right? Now what is the associative property? So for every three elements that A, B, C belongs to Z, this holds, that is A plus B plus C equals to A plus B plus C. So that means we can change the brackets. So therefore associative property satisfies. See, this type of sums we have already discussed in previous sessions, right? Now existence of identity. So for every A belongs to Z, we get this A plus 0 equals to 0, that is 0 plus A. So that means some element plus the identity element, so that we can get the same element. So here that identity element is what? The 0. So A plus 0 equals to 0 plus A, and here there is a correction, it will be A. Okay, A plus 0 equals to A equals to 0 plus A, right? Now therefore identity property is satisfied. Now what about the inverse property, for existence of inverse? So for every A belongs to Z, now for inverse, what we need to check, that is this A plus some B, that will get the identity element, so that is 0. So and we are taking that B equals to A plus minus A. So A minus A or A plus minus A, that we are getting 0, and in same manner if we change the position, the answer won't change. Okay, so therefore inverse property is satisfied, or each and every element has an inverse, right? So it is satisfied. So hence Z plus is a group. Okay, so this is easy. Now let us discuss second example. Show that Q plus is a group. See, the whole example, it is same as the previous one. So the only difference is what? Instead of the set of integers, we have here set of rationals. So it is very easy. So we are just going through. So closure property, everything is same. AB belongs to, instead of Z, we have Q. So we'll get their addition belongs to Q. So that means closure property holds. Now for the associative property, it is also true that if we take any three elements from what? From the set of rationals, and this type of property holds. That means A plus B plus C equals to A plus B plus C, right? So therefore it is associative. Now for existence of identity, it is same. We are getting what? A plus 0 equals to A. There is a correction, A plus 0 equals to A equals to 0 plus A. So 0 is the identity. In same manner existence of inverse, that minus A will be the inverse. So that means A plus minus A equals to the identity. So everything is same except the set, right? So hence Q plus is a group. Now we'll jump to our subgroup question. So that is why we have discussed these two examples, right? So what is the example? See, show that Z plus is a subgroup of Q plus. So this is the question, that Z plus is a subgroup of Q plus. So first of all, what we need to check, so just consider, see, as we know that Z is a subset of Q, right? It is very obvious. by the definition of what we need to prove it is a subgroup. So first we need to check this Z is a subset of what, Q. So it is there. Now also we have seen in previous examples that both the Z plus and Q plus, they are the groups, right? So hence Z plus is a subgroup of Q plus. In exams you have to check all those conditions for all the two sums, right? So hence Z plus is a subgroup of Q plus. Okay, done. Now let us discuss another example. So show that this Q plus is a subgroup of R plus. So I think everything is same. Here instead of Z plus Q plus, we have Q plus and R plus. So just do it at your own. Let us discuss another example. Show that this 2Z plus is a subgroup of Z plus. So this will do. So the solution is what? See, first let us check the closure property. So see, for every AB belongs to 2Z. Now, as we know that this 2Z is a subset of Z, so there is no need to do that. So now what we'll check that 2Z plus is a group, right? So for 2Z plus to become a group, we'll check the closure property. So for every AB belongs to 2Z, we'll get this A plus B belongs to 2Z. So that is very obvious. Suppose if we add this 2 plus 4, then we'll get 6. That is also belongs to 2Z. So therefore closure property is satisfied, right? Now what is the associative property? So in same manner, let take any three elements, that is A, B, C belongs to 2Z. So we have this A plus B plus C equals to A plus B plus C, right? So therefore associative property holds. It is very easy. Now existence of identity. So for every A belongs to 2Z, what we'll do, we get A plus 0 again. We have here A, please correct it. So A plus 0 equals to A equals to 0 plus A. So 0 is the identity element. Okay, so therefore identity property is satisfied. Now for inverse. So for inverse, for every A belongs to 2Z, we have this A plus minus A equals to 0, that is equals to minus A plus A. So this is also done. So inverse exists for each and every elements, so the inverse property is satisfied. So what? Therefore this 2Z plus, it is a group, and 2Z is a subset of Z as we discussed. So hence what we can conclude, this 2Z plus, it is a subgroup of Z plus. So this type of examples can be asked. Now let us discuss another example. Now let H equals to 2Z plus and S equals to 3Z plus. Okay, so the question is union of the sets H and S subgroup? So what we'll do, first let us write what is H, or which are the elements that belongs to H. So H, so as you can see that it is 2Z plus, so all the even numbers will be there. So that means 0, 2, 4 and so on, and for negative minus 2, minus 4 and so on. Now in same manner 3Z, so S contains the elements which are multiple of 3. So 0, 3, 6, 9, here there is a correction here, minus 3, minus 6 and so on. Okay, so H and S consist of these elements. Now we need to check the union of the sets H and S subgroup. So let us take union. So the union will contain these elements, that is 0, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. So that means all the even numbers as well as all the elements which are multiples of 3. So this union contain that elements. So now consider, see, we need to check the closure property, but actually it does not hold. So we need to give the counter example. So consider A equals to 2 and 3. So as you can see that 2 and 3, they both belongs to the union set, but we have the operation plus. So if we add them, so that is 2 plus 3 equals to 5, but that does not belongs to the set H union S, right? So see, as you can see that this 5 does not belongs to the H union S. So what we can conclude, so therefore the closure property fails. So as the closure property fails itself, so no need to go for the associative identity and inverse property, right? So this sum is done here. So what we can write, the union of H and S is not a subgroup because it does not satisfy the closure property. Now the important result based on this example, so the intersection of any two subgroup, it is a subgroup. Okay, but the union of two subgroups is not necessarily a subgroup, and the counter example is this, right? So if we take two sets which are subgroups, and if we take their intersection, then it will also become a subgroup. Okay, but for union it is not necessarily true, right? Thank you.